Our team is seeking to examine efficiency in small-scale regenerative braking systems, such as an electric skateboard. Our project tests various procedures to better understand how to optimize efficiency. We used the potential energy of reams of paper to act as an energy input and calculated the losses to get an accurate idea of the efficiency. The weight provides a predictable quantity of potential energy into the system. We used a power resistor as our load to measure the energy output, while our motor was in regenerative braking. Power resistors safely dissipate large amounts of power into thermal energy. Its resistance can be selected directly. Our presentation will cover background information, a detailed explanation of our circuit, an analysis of our results, potential sources of error, as well as future applications and next steps.
So what exactly is regenerative braking? Regenerative braking is an energy recovery process that slows the electric vehicles by converting the wheel's kinetic energy into electrical energy, which is then stored in the battery. When you decelerate, the electric motor stops supplying power, so the vehicle shuts down. This disengages it and runs backwards, making it act like a generator. The purpose of this is to recover energy that would have been lost as heat caused by the friction between the braking pads and the brake. The benefits of regenerative braking include an increase in fuel efficiency because the energy that is lost can be recovered to power the vehicle, longer range due to an increase in battery life from regenerative braking, and then finally, it reduces wear on vehicle components, especially the brake pads. The first stage is to prepare the apparatus by starting with the cord coiled around the motor, attaching the weight to the cord, then raising the weight up to a height greater than 3 meters, which is then suspended by the motor. Next, to enable regenerative braking, power the motor controller with a power supply of at least 30 volts, which is the minimum for the motor controller. Set the motor controller to maximum braking. Then once you're ready, release the weight so it begins to free fall. Almost instantly after that, turn off the power supply and enable the load resistor to allow the current to flow. Finally, measure the voltage across the load resistor and shunt. Record both values every half a second.
Nice!
Before testing, the circuit should look like the one shown here. This has the power supply turned on, which provides an initial voltage to power the motor controller, and have the shunt in series, ready for measuring values. However, it does not impact the power going to the power supply because the resistance is negligible. During testing, once the weight is dropped, switch the power supply off as the motor controller is now being powered by its own regen power. Flip the switch instantly to connect the load, meaning that the current will begin to flow in the opposite direction through the load resistor. Current then flows through the shunt, which is a precisely known resistance that we can use to find the current.
The heights and weights were measured over time to calculate the power into the system. We filmed the drop and read the height off of a tape measure. We calculated the energy input by multiplying the height and total time by acceleration due to gravity. Air resistance and friction were neglected. The shunt and power resistor voltages were tabulated by filming the values off a multimeter while noting the time in the video. The current through the shunt was calculated using its known resistance, and it was multiplied by the voltage to get the power through the shunt. The power through the load was calculated by multiplying the voltage across the load by the current through the shunt. The instantaneous output power is the sum of the power through the shunt and load. Integrating the total power output over time using a trapezoidal Riemann sum, we calculated the total energy recovered for each test. Here's an example of a test with 1 ream of paper and 3 ohms. Dividing the total energy output by the energy inputs gives us our efficiency. We observed peak efficiency at 3 ohms.
All right, so what can we learn from this data? Well, firstly, we saw that for this size of motor, the size that you could conceivably fit on a skateboard or a scooter, we can expect approximately 40% energy efficiency of energy being able to be recovered. We also saw that for this setup, the best efficiency occurred when we had a load resistance of about 3 ohms And finally, we also did not notice any significant changes in efficiency with different amounts of weights we tested. This means that inputting different amounts of potential energy into the system doesn't seem to yield any better or worse efficiency.
Any measured process has some potential for error. We tried to control as many variables during our test runs to reduce the number of sources of error and minimize our measurements uncertainties. Our known instrumental uncertainties were the voltage uncertainty of the shunt and the load resistances, and the shunt's resistant error rating. Using the multimeter's manual, we found that our ratings uncertainties would be 0.5 and 0.8%. Using the internet, we estimated our shunt's uncertainty to be of 0.5%. Our estimated observational and measurement uncertainties were that of the height of the onset of braking, of the time of regenerative braking, and of the mass of the system. Using video recordings of all 36 system drops, plus basic video editing software features, we found our estimated uncertainties across all tests to be 5 centimeters for the height of drop and 0.01 seconds for time. The masses uncertainties were all 0.25 kilograms, which we estimated using a personal analog scale. We were not able to account for some uncertainties, and even some variables, in our experiments. The variables we could not account for were the air resistance acting on the falling system, the internal friction of the motor's mechanism, and the speed at which the regenerative braking was activated. Because we could not account for these variables, we also could not find how much uncertainty they introduced into our measurements. This means that we have no way of knowing how much those variables affected our results. We believe their effects to be negligible, however, as well as the effects of the cable's weight, the controller's resistance, and the circuit's temperature. To calculate the uncertainty propagation at each step of our calculations, which means after any equation is applied, we use the standard variance formula. Across all steps, we used Excel to calculate many individual uncertainties, which in the end resulted in 12 efficiency uncertainties, one for each test we conducted. The average efficiency of the most significant test was of 40%, and this final efficiency's corresponding uncertainty came out to be 3.62% of that 40%, which translates to a range of confidence of 40 plus or minus 1.13%. Therefore, the efficiency of the most significant test was at least 38.87% and at most 41.13%.
Understanding how the regenerative braking system works and adjusting the magnitude of these regenerative brakes is crucial to maximizing the efficiency for any type of application. Common transportation devices such as skateboards, bikes, and scooters are a more popular application of these regenerative brakes. However, the tests we conducted used vertical constant force, which is different from the horizontal movements and various acceleration of these vehicles, so our testing methods may not be accurately represented. The major application of our testing method of regenerative brake systems are elevators. Since our testing method involves capturing the potential energy as we drop a mass, this has a strong correlation to as of an elevator. While mass is a less to no effect on efficiency itself, velocity of an elevator is a crucial factor when considering safety. In order to maximize efficiency while being safe, we propose of an elevator with a weight sensor which could adjust the amount of load for an ideal efficiency at a safe enough speed going down.